Hello everyone, thank you Cosmin. I am Visala from Facebook Infra ASIC team. I joined Facebook 2 years ago. My work here focuses on the hardware solutions for video transcoders and other video pipelines. Today, I'll be giving an introduction to hardware acceleration by energy efficient transcoding. Our agenda also includes cross-codec and HDR encoding, quality metrics, architecture, and results and conclusion. In Facebook, billions of videos get processed here both at Facebook and Instagram every day. Each uploaded video is typically viewed on various devices under different resolutions and bandwidths. The input user upload video may or may not be at its best quality. So it becomes very critical that any processing done by Facebook servers does not lower the input quality of the videos. How is this done? Let us now look at the typical video transcoding flow at Facebook. The client uploads videos. A decoder that supports multiple codec standards then decodes the video. The decoded video is now the FP original, is then scaled to multiple resolutions by a scaler. The scaler is very generic and can perform upscaling or downscaling operations. The scaled videos are then encoded by an encoder. The encoder is tuned for very high quality. They are also encoded at multiple bit rates. The current software encoder supports H.264, VP9, and AV1 standards. Then the quality scores are measured at the input to understand the quality of the uploaded video. Then for each encoded bitstream as compared with its original, which is called the playback quality score, and the quality score for the encoded bitstream independent of the original, which is called the overall quality score of the video. All this is then used by the ABR, which is adaptive bitrate streaming, to dynamically decide on which video is sent to the user based on the user's environment. In this flow, the encoder, which has a very deep pipeline, and the quality measurements, which are pixel-based, consume a lot of CPU cycles, and hence a lot of power. By using hardware acceleration for the decoder, scaler, encoder, and quality measurements, we can save about 30 megawatts of continuous power. Encoder optimizations are chosen such that the compute is reduced while we preserve quality across multiple codecs and to efficiently process the HDR input. With this, I now hand it over to Gaurang to talk about the cross-codec and HDR encoding.
Thank you, Visala. Hi, everyone. My name is Gaurang Chaudhary. I have been at Facebook a little over 2 years, and my work is centered around video encoding optimizations, algorithm complexity optimization, and mapping algorithms on hardware. At Facebook, we employ multiple codecs like H.264, VP9, and AV1 in the video pipeline, and it becomes important to always look for optimizations in the system. These are the few possible video encoding optimizations that we want to discuss today. Cross-codec optimizations help to reduce encoding computational requirements of supporting multiple codecs. 10-bit encoding optimizations, that is using lower precision data path for compute-intensive blocks like motion estimation and mode decision. Both of these techniques helps in software encoding and also in the hardware ecosystem. Next slide, please. We presented the paper on cross-codec data sharing in SPIE Applications of Digital Image Processing 2020. Cross-codec idea is to share the decisions of most compute-intensive blocks, motion estimation, and mode decision data from one codec into another, thereby saving the computational requirements of the system. This can be effective when a new codec is an evolution of older codec, such as VP9 to AV1, where more tools are added to realize bitrate savings for the same quality. Cross-codec data sharing can be done completely in software, or if someone is planning for specialized hardware for few codecs, a hybrid software-hardware solution can be utilized where hardware-generated data can be hooked up to a software encoder for the newer codec. Many VOD systems employ a convex hull approach to decide the best rate control settings for encoding. This is another avenue where cross-codec data can be shared. It can also help with ASIC implementations for multiple codecs. Next slide, please. So what type of data can be selected for cross-codec data sharing? The qualified data to be shared should satisfy at least one, if not all of the following. It should be compute intensive. It needs to conform directly or through a mapping with the standard normative requirement of the target codec. The coding inefficiency is acceptable after reusing this cross-codec data. The overhead it generates to the target codec can be absorbed seamlessly. Next slide, please. These are some of the results with cross-codec optimizations of sharing VP9 data for AV1 encoding. We present results for the Facebook internal dataset, which are 400 top viewed public videos from the Facebook pages and has video contents across different resolutions. These show coding efficiency results using VD rate with respect to three popular video metrics, video quality metrics, the SSIM, PSNR, and VMAF. All comparisons are made with Anchor as libvpx 1.8.0 at CPU speed 1 preset. The vertical axis is the BD rate delta percentage, where the negative values indicate it is better than the Anchor, and the horizontal axis is the different versions of VP9 AV1 encodings. The first column set shows that our internal VP9 experimental codebase is close to libvpx 1.8.0. The second column set shows BD rate reduction of libom 2.0.0 at preset CPU speed 1. As expected, AV1 has significant gains, 30 to 35% compared to VP9. The third column set shows the quality of VP9 AV1 equivalent encoder, that is the AV1 toolset equivalent to the VP9 toolset. It is interesting to note that even without computationally expensive features, we can get good gains 10 to 16%, which comes from the better design of intra-inter modes, adaptive entropy coding, inter-referencing structures, and post-processing filters. The last column shows the results for AV1 VP9 share quality, which is where we are using the cross-codec data, that is the VP9 motion estimation and mode decision data for the AV1 encoding. Overall, we still get a gain of 5 to 10% compared to VP9 libvpx 1.8.0 at CPU speed 1 with very little additional computations. Next slide, please. This slide shows the results for the widely accepted JWeight and DERF datasets, and we see similar results for the cross-codec data sharing. The results on DERF dataset are similar to what we see in FB internal dataset. For JWeight, we see slightly better results from the previous slide. Content-wise, both these datasets have good coverage of different types of videos based on complexity. Next slide, please. We can extend the encoding optimizations to 10-bit encoding. Our solution is to replace the compute and power-intensive blocks in high bit depth encoding, like the motion estimation, the mode decision, etc., with the lower precision, that is the 8-bit versions. We tried this experiment in VP9 to demonstrate the concept of using 8-bit versions for 10-bit encoding. Advantage of doing this is primarily the power savings, and secondly, the agnostic architecture for hardware implementation. That means lesser design and verification cycles due to the same blocks getting used in higher bit encoding. Next slide, please. In this slide, we want to highlight some of the key things we used in our experiment. The CRF QP values, the two different video quality metrics used for the BD rate evaluation are SSIM and PSNR, and all comparisons and experiments are made with respect to VP9 internal experimental code base at CPU speed 1 and at constant quality rate control mode for VP9. Next slide, please. In this slide, we show the results of our experiment. The vertical axis is the BD rate delta percentage, where the positive values indicate it is worse than the anchor, and the horizontal axis is the different datasets used in our experiments. The blue columns shows the BD rate delta with SSIM as the quality metric, and the orange columns shows the BD rate delta with PSNR as the metric. As we see here, by replacing the compute intensive blocks in 10-bit with lower precision 8-bit versions, the loss in quality is around 2 to 6% across different datasets. Next slide, please. In this slide, the vertical axis represents the BD rate delta with SSIM as the metric, that is the blue columns from the previous slide, along with the percentage encoding times on the horizontal axis. We observe that while the trade-off in quality is around 2 to 6%, the encoding time is significantly better, around 22% better across multiple datasets. If compared to libvpx CPU speed 2, which is around similar encoding time, the quality is still roughly 2% better. One thing to highlight is even if the quality is on par, the hardware reductions are something that are irreplaceable and overall provide power savings over using lower speed preset for libvpx with full 10-bit encoding. If we consider convexal approach, using lower precision data path for 10-bit encoding can give us significant computation and power savings. I would now like to hand over to Deepa for discussion on quality metrics. Thank you.
Thank you, Gauram. Hi all, I'm Deepa Palamadai Sundar from Facebook Infra ASIC team. I joined Facebook about a year and a half ago, and my work focuses on hardware acceleration of video quality metrics. Now that we've seen the hardware improvements for the encoding operation, let's take a look at why a similar strategy would work best for quality metrics as well. Quality metrics is often very complex and it's computed for a wide range of viewport resolutions. Most of these metrics require a per pixel computation, computing components like the local mean and variance, using very elaborate or wide filters like the Gaussian and Sobel filter, using operations like the logarithm operation, also the requirement for very high precision using floating point arithmetic. All these make quality metrics extremely compute intensive, which can consume most of the available resources if it's done in the software pipeline. Here, we show an example of FFmpeg execution times for different viewport resolutions. We are comparing the time taken to do the encode, decode, and QM operation. Here we use the VMAF score compute for the quality metric. We can see that the quality metric takes more time than the encode and decode operation put together. And as the resolution increases, the computational complexity increases and the time as well increases exponentially. So hardware acceleration would offer a more energy efficient solution in this case to compute these quality metrics. Next slide, please. Here we propose a high-level architecture to compute these quality metrics in hardware. Quality metrics in general are classified as full reference, reduced reference, and no reference metrics based on the availability of a reference image to compute the scores. The proposed architecture can support both full reference and no reference metric algorithms. The two main components of this architecture are the DMA controller and the compute kernel. The DMA block is used to fetch the input frames from the memory, and the compute kernel is the one that actually computes the various quality metric scores. Next slide, please. Here are some of the most commonly used full reference metrics supported by the hardware. The first one is the PSNR, or the peak signal to noise ratio, which computes the pixel-wide difference in luminance and chrominance components. The second is the structural similarity index. Here we support two versions of the algorithm. One is the libvmap version, which is same as the original paper. And the second is the FFmpeg version, which is an approximation using the overlap 8x8 window algorithm. Next slide, please. The third is the multi-scale SSIM or the MSSIM metric. This is computed for 5 scales and it uses operation like the Gaussian filtering. The fourth is the VIF or the visual information fidelity. VIF scores are part of the VMAF metric and this is computed for 4 scales. Along with the full reference metric, the no reference blurriness metric score is also supported by the proposed hardware. Next slide, please. The compute kernel is the heart of the accelerator. To help with computing metrics simultaneously, we use 3 independent kernels, namely the FFmpeg, the SSIM, and the blur kernel to calculate the SSIM, VIF, PSNR, and the no reference blur scores. This helps us not only to speed the compute, but also saves bandwidth and thereby power. As these metrics are also required to be computed for a wide variety of viewport resolutions, we will need some scaling support to upscale or downscale the input frames to the required viewport size. The proposed architecture also offers inline scalars to do the scaling operation. This will further optimize the bandwidth as it avoids the need to read and write the scaled outputs to and from memory. Additionally, we can also compute block level scores within the frame, and this is extremely useful in identifying regions that have higher impact on quality scores during the encoding process. Now, I hand it over to my colleague Cindy to go over some experimental results and conclude this talk. Thank you. Hello, this is Cindy.
Thank you, Deepa. Hi, my name is Cindy Chen, and my work over the years at NVIDIA, Intel, and now Facebook has been focused on a hardware-friendly algorithm for image processing, computer vision, and computer graphics. The first experiment I will describe compares the read bandwidth used in between a software implementation on the CPU and the proposed hardware architecture. We look at the case where we need to compute the following three metrics: SSIM, PSNR, which needs both the reference and distorted frames, and the blurriness metric, which only needs the reference frame. As you can see in the table, in a CPU-based software solution, the same input frame will have to be read again to compute a different metric, so a total of 3 reads for the reference frame and 2 reads for the distorted frame are needed. In our proposed architecture, input images only need to be read once, and the 3 metrics can be computed in parallel. This greatly reduces the bandwidth needed and therefore is more energy efficient. The larger the resolution, the more energy efficiency we will achieve. Overall, we estimate that using the proposed architecture could improve the performance per watt by 100 times comparing to CPU-based solutions. Next slide, please. Our next experiment focuses on algorithm modifications that are needed for hardware implementation. The original CPU-based software algorithm cannot be implemented as is in hardware due to a few challenges. For example, full 32-bit floating point arithmetics on CPU is very expensive for ASIC. Complex mathematical nonlinear functions requires hardware-friendly implementations due to limited area precision and timing. We also need to minimize the number of divisions and applications as they require more hardware complexity and thus more power. Let's take the most complex metric we propose to accelerate, the VIF metric, as an example. The diagram on the right shows the software implementation flow. The original image and the distorted image come in. Let's call them image A and B. First, 3 additional derived images have to be computed: AABB and AB, where AABB are squared of the original images, and AB is the pixel-wise product of A and B. These images are then filtered by a Gaussian kernel, which is how we get the local mean and variances. The VIF score for that scale is then computed using a bunch of multiplication, division, and logarithm operations. These 5 filtered images are then decimated by 2, and similar process will repeat, so we get the VIF score for the next scale. So to do this in hardware, we propose to use fixed point representations everywhere floating point is needed. This includes the Gaussian filter coefficients, the low-pass filter used in decimation, and all intermediate results and final scores. A hardware-friendly approximation is needed also for the base 2 log computation. All these approaches will cause some precision loss, which means numerical issues would more likely to arise, and we need to handle them appropriately, such as clipping the variances to non-negative. Next slide, please. So in order to compare how our hardware-friendly implementation compares with the reference software, we built 2 simulation models, the floating point model and the fixed point model. The fixed point model contains all the hardware-friendly alternations we described, which include fixed point representation, approximation to the log functions, and various numerical stability guards. The floating point model is built by directly taking the floating point score computation functions from the reference software and put them in the same test harness as the fixed point model, so both models receive the same input images. We then feed 400 sequences of video and their transcoded versions to these 2 models. We then compare the difference between the scores reported by these 2 models. Next slide, please. So the table summarizes the average absolute difference between the scores reported by the 2 models for 4 metrics. We group the errors by video resolution and the QP value used in transcoding. It can be seen that the average error for the fixed point implementation ranges from 0.000004 for FFmpeg-based SSIM to less than 0.015 for VIF. The larger error for VIF is due to the complexity required in the score computation, such as the logarithmic function. These errors are deemed to be acceptable by our video software team since they are small enough and could be calibrated out by retraining the model using the overall VMAF score computation. Next slide, please. To conclude, hardware acceleration can tremendously improve the energy efficiency of video transcoding systems at scale. The proposed quality metrics architecture can greatly improve the performance per watt of objective quality metrics computation compared to CPUs. The proposed architecture can be further extended to use chroma channels and also to compute more complex metrics such as the full VMAF score. Also, leveraging encoding decisions not only reduces the overall compute complexities, thus power, required in the transcoding system, due to the small data path width and less memory usage. This approach is especially beneficial for hardware implementation since it also reduces verification space and design complexity. This gives us motivation to explore more creative ideas in this space for future work, such as tuning the first pass statistics in video transcoding. This ends my presentation. Thank you for your attention. I will now turn it over to Yanni to start the panel discussion.
Thank you.